Afternoon, everyone, and welcome to this UCL Minds Lunch Hour lecture. We are pleased to have you all with us today. My name is Adnan Mehanic, and I'm a lecturer in EEE department here at UCL. That's for Electronic and Electrical Engineering. And today I have a privilege to introduce Dan Mannion, who is a PhD candidate and then studies the use of novel electronic devices in bio-inspired computing. Dan has spent a lot of time at EEE department, and for the last 5 years, he has been working on neuromorphic engineering. The long-term goal of this research is to reduce the power consumption of machine learning hardware that we are using today. More specifically, the approach is to try to do this by taking some of the inspiration from the human brain. Dan has recently developed circuits to implement edge detection of an image in real time using minimal computations and elements. And for this work, Dan got awarded with the Neurotech Prize. Dan also collaborates with Birkbeck University, working to conserve pieces of art and cultural heritage. And in this role, he has been worked with Tate Britain and Mary Rose Trust. So I believe you should all have got the summary and abstract. So I'm not going to repeat and read all of this, but I believe that Dan is going to talk about neuromorphic engineering. Why is this quite a timely important subject? And what is the challenge that this technology could solve? So before I hand to Dan, I just want to remind you that you can post your questions on the platform Slido, that is sli.do. And if you use the code LHL2, that is LHL2, you should be able to put your questions there. And then after Dan's presentation, hopefully we get to hear some of these answers. So with that, I hand over to you, Dan, and yeah, please feel free to start.
Brilliant. Thank you very much, Adnan, for the introduction. So as Adnan said, today we're going to be talking about neuromorphic engineering. Now, for some people in the audience, the word neuromorphic might not mean very much, and that's okay, because by the end of today's presentation, hopefully we'll have a better understanding of what neuromorphic engineering actually is, but most importantly is why it's needed. And fortunately, neuromorphic engineering, although we may not have heard about it, it relates to something everyone should have heard of, which is machine learning. So we're surrounded by machine learning, and sometimes that can feel a bit overpowering. It seems like we've potentially been outcompeted in a lot of computational problems. So today, I also kind of want to dispel that notion and reveal the curtain and show you some of the challenges and the weaknesses that machine learning struggles with. Because in fact, you as a human are far superior to many machine learning implementations when it comes to the efficiency of your thoughts. And in fact, machine learning actually has to learn a lot from you and be inspired from you if it wants to be scalable and more ubiquitous in everyday life. So, yes, oh, okay, sorry. Sorry, just got a little comment, making sure I'm going to share my audio in a minute. But before we get into that big ego boost for yourself, I'm going to do that later on in the talk. I want to go right back to the beginning and make sure we have a shared understanding of where machine learning is and some of the challenges that it faces. Once we understand those challenges, we'll get to the second part of the talk, where we'll get into the technical details, what's actually causing these issues. And then finally, at the end of the talk, we're going to touch on one solution to this problem, which is neuromorphic engineering. So I'm going to bring up the slides now. And I hope all of you can see that now. And we'll get going. So in order to get an idea of where machine learning currently is, we can start with a project which some of you may have heard of, which is AlphaGo. So AlphaGo is a Google project, and the task was to learn and excel at playing a game called Go. What is Go? Well, Go is a game kind of similar to checkers in that you have white and black pieces, but the pieces are placed on an intersection of the grid, and the objective is to surround the enemy pieces so that you can capture them. And it's a game which is considered to require both skill, but also creativity. So it's an interesting game to pick. And this project has been phenomenal in its success. It was able to beat the grandmasters of the game, some of the grandmasters, at a global scale, and has got to the point where it's generally considered unbeatable by human players in the long run. So it's a phenomenal story. And if you want to know more about it, it was featured in this movie, which you can go away and have a watch if you want to learn more. But that was actually quite some time ago. And since then, those kind of projects have evolved to the level where it removed all form of human inspiration. So take, for example, one of their latest projects, AlphaZero. So AlphaZero has got rid of any kind of human input initially. AlphaGo, the earlier example, initially learnt by studying games between humans, human versus human matches. And it took inspiration from that. AlphaZero has got rid of that completely. It plays against itself. Initially, it's atrocious, it's terrible, it's useless. But each game, it gets better and better and better. It plays against copies of itself until eventually it reaches a level deemed a grandmaster level. And so this flexible approach has been applied to a lot of games. So this kind of reiterates the idea that when we look at machine learning demonstrations such as this, it's kind of a bit worrying. Like, are we becoming useless? And the point is that we should actually be cautious when we see these results, because what we see are the results, the successes, but what we don't necessarily see is how those successes are actually attained or achieved. And this is important because these kind of successes rely on both the development in software and algorithm and machine learning principles, but also on hardware. And the hardware is usually hidden from us. It's not necessarily shown. And the reason hardware is important is because in this context of playing games, you could almost see hardware as the equivalent of doping in professional sports. The more hardware I have available, the more power I inject into the machine, the more searches the algorithm can do, the machine learning entity can do. So what do I mean by searches? Well, imagine you're playing chess or some other game, and you can ask yourself, well, what happens if I make this move? Does that give myself or my opponent an advantage? And I can go one step further, and I can say, well, having made that move, if I then make this move or that move or that move, does that give my opponent an advantage or does it give me an advantage? And so by asking myself these questions, and by continuously asking myself these questions, I form an almost branch-like or tree-like representation of my next move. Now, as a human, we can only store and memorize so many of those representations within a time frame. And obviously, a grandmaster in a game can hold more of those representations than I could. And when it comes to computers, if I chuck in more hardware, then it gives them an artificial advantage because they can also carry out more of those searches, potentially outperforming a human. So, and we can also see this in the data. If we take a look at this table from a paper from the original AlphaGo publication. So what this table is summarizing is the amount of hardware that AlphaGo used and its ability to play the game, so its score, how well it played. So the key columns to look at are these two tables in the middle and the one at the end. So the two tables in the middle represent and show how much hardware is being used. So it's using CPUs and GPUs. If you aren't too sure what these kind of things are, don't worry too much. We can essentially consider them to be roughly the same thing. They're the brain of the computer. And as we go down this list, we go from a relatively moderate number of CPUs to GPUs down to where we're using thousands of CPUs and GPUs. So in this lower half of the table, we're using much more hardware and in turn consuming much more power. And then it's no surprise then, if we look at this far right-hand side column, which gives us the score and how well it plays, that its score increases as we increase that hardware. So this is a number which represents how well it's playing Go. The higher the number, the better it's playing. So we can see at the bottom here where we have the most hardware, we're getting the highest score. Now, of course, these high scores are a result of both software changes, but hardware change does drive this. And we can take a look at an example with one of the games that were reported for AlphaGo, which is the game against Fan Hui, which is described by this bar chart at the beginning. So what we're seeing here is a rough figure of how much power the ideal hardware would consume in lots of different versions of AlphaGo. So we're going to come back to this section later on in the talk. This is where we start to an improvement, and we'll address this later on. But for the time being, I want you to look here. So this is the early days of AlphaGo, playing against Fan Hui, one of the masters of Go. And we can see that actually the picture of a human versus one computer can be misleading, because the actual hardware involved in this game wasn't one computer, but it was over 1,000 CPUs and over 100 GPUs. So the image of one human, one computer, it's really against almost thousands of computers, if you assume roughly your laptop has a single CPU, potentially a GPU. So there's this a big disparity between the amount of hardware being used and the against the human. Another figure of merit we could use to gauge how fair a fight this is to look at the actual power consumption in watts. How much energy does a human consume against a particular AlphaGo implementation? So let's start with the human. It's roughly agreed upon that a human consumes about 100 watts at rest. And your brain itself uses 20% of this. So we can assume that Fan Hui, when he's playing AlphaGo, is consuming about 20 watts, probably slightly higher because he's obviously not at rest. And to put that in context, 20 watts is slightly more than an energy efficient light bulb. So when we know that, we can ask the question, well, okay, how much is AlphaGo consuming? Well, it's widely reported that in the game against Fan Hui, which is shown here, and this is Fan Hui, and this is Fan Hui's human interpreter, so to speak. No, sorry, AlphaGo's human interpreter. AlphaGo was consuming around approximately a million watts, which is a megawatt. So that's interesting, because what that shows is a hidden disparity. The human is operating at an incredible level of Go performance at 20 watts, while AlphaGo in this match was consuming almost an industrial scale. So when we see images like this, perhaps these little graphics are a bit more accurate. Light bulb versus industrial scale power consumption. Now, this is one example, and we might not all be too interested. It doesn't affect our lives, the games of AlphaGo Masters, but we're also being cheated a bit closer to home, and that's in the form of our phone. If anyone has Siri, there's an example that exists there as well. So when we use Siri, it's tempting to think that everything Siri does is carried out on the phone. I say, hey Siri, it wakes up, it searches whatever question I ask. But actually that's not true. So for example, when I say, hey Siri, what's actually going on is the phone is in a low power mode, and it has a bit of hardware that does listen to the audio and try to detect when you say those words. But when it's finished analyzing that speech, it's not entirely certain. What it has to do then is to take that audio recording, send it off to a server run by Apple in the cloud, and then the server then carries out a more detailed analysis on your Hey Siri command. If the more detailed analysis says, okay, yeah, you did say Hey Siri, then it lets the phone know, and the phone sends off your question off to the server to be analyzed, and then results sent back to your phone. So actually, when you look at the big picture, only a small part of Siri is carried out on the phone. And the reason for that, as you probably can guess by now, is one of power consumption. If you want your phone's battery to last throughout the day, you cannot be running intensive machine learning tasks on it while listening to pick up the odd two words. So these are a couple of specific examples, but it's not just an issue at the individual level, but power consumption within machine learning is becoming a more global environmental concern as well. So there's a very interesting study on deep neural networks, particularly the kind of deep neural networks which analyze a lot of text and then can generate text based on that. And these are called natural language processing neural networks. So when one is actually in operation, it's not producing too much CO2, as we can see at this point in the table. However, a machine learning neural network has a long lifespan. It's being operated, but before it was being used, it was being developed, tuned, and experimented on. So when we zoom out and take into account all of the entire lifespan of that model being developed, This study found that the CO2 produced for one particular network could produce the same amount of CO2 as a human living 7 years of their life. So with that, what we see is that actually on a global scale, the inefficiencies of some machine learning hardware is becoming an issue, and we need to fix it as we move into the future. So we see there is a problem with machine learning and power consumption now. The question is, what is causing that? Why is this happening? And that brings us on to the second part of the talk, which is all about the problem. What is causing these inefficiencies? And so for that, what we have to understand is have a basic understanding of how computers compute. So the vast majority of your computers use an architecture called the von Neumann architecture. The basis of this is that your consistor can be thought of as two separate components: memory, which stores information, and a processor, which acts upon that information. Now, the processor is essentially the brain of the computer. It can add numbers, subtract, multiply, and it can do more complex things, such as comparing two numbers together, comparing it against zero. Now, this architecture works really well when you're running generic computing problems, but there is a slight issue with the architecture, and that's the fact that information has to be transferred between the processing section and the memory. And this transfer of data can become an issue if you need to do it too frequently or the transfer isn't fast enough. It ends up becoming a bottleneck. And because this bottleneck is intrinsic in this kind of computing architecture, then we name it after the architecture and is often referred to as the von Neumann bottleneck. Now, for general purpose computing, this isn't too much of a problem. The reason why it becomes an issue in machine learning is that the majority of machine learning models relies on particular mathematical operations, which send data back and forth repeatedly at a high intensity and a high rate. And because we rely on those operations so much, we really suffer from this bottleneck. Now, one of the big issues with this bottleneck is the fact that it's not actually getting better with time, as we can see from this data here. So what we're looking at here is a plot of your processor speed, so how quickly the processor can carry out operations, and we're comparing that against how quickly memory can be read from and written to. So we're basically looking at how fast those two elements can operate, the two elements of the von Neumann architecture. And we've got data here up till 2000 and also 2010. So let's look at each element individually. For the CPU, we see a really steady increase in performance. It gets faster and faster with each year. We've seen in the last 2 decades that is starting to taper off. When we look at the memory, however, how fast we can read and write to the memory, we get a different story. Although it is having a steady increase in its read and write speeds, it's not at the same level as the processor. So what that means is our processor can compute really fast, but our memory is not able to supply data for it to be processed fast enough. And now what the problem with that is that you get this divergence in performance, and it's referred to as a performance gap. And this ends up being a real limitation. The argument for why this exists is down to the priorities of the research. With the CPU, the fundamental priority is faster. We want it to compute as quickly as possible. With memory, it struggles because there are two priorities. We want it to be able to operate faster, but maybe more importantly, we also want to store more. And we've seen a phenomenal growth in memory density over the decades. So it's no surprise that we had to compromise on read-write speeds. So what we see from these graphs and what we really want to take away is that this bottleneck isn't getting any better. And if machine learning really relies on this kind of limitation, we need to work our way around it. Now, how do we do that? Well, the solution actually can be hinted at if we go back to AlphaGo. So you saw this graph earlier, and we talked about Fan Hui's game, and we saw that it had quite a high power consumption. Well, then if we look in the game that followed that with Lee Sedol, and then future versions, we can see a really significant reduction in the power consumption of the architectures. And this is promising. The question is, how did that occur? And the solution is indicated in the bottom here. So initially, Fan Hui, the system against Fan Hui, involved using a bunch of CPUs and 176 GPUs. In the Lee Sedol game, they're using something else. They're using what's called a TPU. Now, as the name suggests, it's very much like a CPU and a GPU in that it's a processor. It carries out operations. And here is an image of a TPU. It's just another bit of a computer. The difference, though, with the TPU is that it's specifically designed for machine learning operations. So there are those mathematical operations we talked about earlier, which were so intensive on that bottleneck, can be accelerated and made more efficiently using the TPU hardware. So what we're seeing then is a progression from generalized computing to more specific computers that are more specific to their application domain. And this isn't surprising because the GPU down here is also the result of that kind of research trend. Originally, the original solely CPU structure couldn't render graphics fast enough, so GPUs were invented to address that problem. Now we're finding that hardware can't do machine learning, so things like TPUs are being developed. So the general trend from generalized computing to more application-specific computing is definitely a way to go. So this is essentially how we solve that. One way to solving that problem is that we need to develop more machine learning-centric hardware. And the TPU is one approach. But in this talk, rather than going down that route, I'm going to take you down another one, which is the field I work in, which is where we take inspiration from yourself, from biology. And that's where neuromorphic engineering comes into play. Essentially, it's the idea of building circuits and computers that are inspired by the neurons and the makeup of your physical brain. So, how does it work? Well, in order for us to understand neuromorphic engineering, we first off need to understand how the brain computes. So there's no getting around. This is an incredibly complex topic. So from a neuromorphic perspective, what we do is we take a simplification. In order to replicate and build systems, we have to make them slightly more simple and more abstract. So your brain, from our interpretation, largely consists of neurons, which are the things that are the processors of your brain, you could say. They receive inputs and they produce outputs, which are voltage spikes. And we can see, which is pretty cool, an actual neuron which has been grown on a substrate. So these are artificial. So in this top figure here, this large bulbous patch is the neuron. So this is the thing that would read inputs and produce a spike in voltage, depending on its depending on the inputs. And all this kind of meshy stuff is dendrites and axons. It's how you get signals from one neuron to the other. And so your brain consists of all these neurons interconnected with each other. And the connections are very important. The connections are illustrated here, and we refer to them as synapses. Because when you're transmitting a signal from one neuron to the other, it's not transmitted perfectly. Instead, what this synapse does, or this junction, the junction between the two neurons, what this synapse does is it transforms that spike slightly. And that can be through multiple ways. You could make the voltage spike smaller, or you could make the voltage spike broader, but it transforms it. And that transform is important because it's how we carry out some data like transformation or processing, and it's also how we store memory. So if we want to build computers that are based on memory, the two fundamental components that we need to replicate then are the neuron and the synapse. So the question is, how do we do that? And we're now going to look into that. But just before we get there, if anyone, from people who come from a machine learning background, you may at the moment be thinking, this actually seems quite like your standard machine learning model. You have a neuron and you have synapses in between and weights. And so it seems very similar from an architecture perspective. The difference, however, is in the encoding of data. So in a normal neural network, that encoding is usually a numerical form from, let's say, 0 to 1. It's a constant number. But in biological systems, you don't really represent information by numbers, but the output is a spike. You represent information with spikes. This is an example of one voltage spike that a neuron might create if it's excited with an input. And this is a whole train of neurons. So you're looking at the output of one neuron and how it changes with respect to time. And these spikes can have incredibly rich dynamics because you can encode data both in the amplitude, in the shape of the spike, and also in the frequency of them. So we see here in this figure a variety of frequencies. Here we have quite a low frequency. There's only 3 within a given time. Here it's much higher, and it's what we call a bursting response, a very tight collection. And in this gap, there's absolutely nothing going on. And this is very interesting when it comes from a power consumption perspective, because a normal computer is churning away power almost continuously. Whereas in a spiking neural network, you can have a neuron not doing anything and consuming very little power in this idle state, even though it's part of a much larger, busier network. So that's very interesting from a power consumption. The question is, though, are we actually able to replicate these kind of behaviors? Can we get a neuron circuit to do this? Well, the good news is, yes, we can. So neurons, or models of neurons, circuits of them that have been built from your standard transistors, your basic electronics components, have existed since almost the founding of this field. And there's a whole variety of them. This is just one example. So we won't go into the details of how this circuit works, but essentially it's a pretty standard electronic circuit operating in the analog domain. So rather than zeros and ones, we use any voltage in between those two levels. And by injecting an electrical current into it, you can produce these output spikes that we saw earlier. So an example of some of the spikes that this kind of circuit produces is shown here. And what we see is that depending on the input current and depending on the settings of the neuron, we can actually produce really wildly different spike trains. And when we compare that to the biological spike trains that we saw earlier, we can see that actually we're getting very close and essentially replicating the kind of outputs we need a neuron to be able to do. So we can essentially consider neurons done and dusted. The remaining part then, we have our neuron, the remaining part is our synapse. Are we able to replicate the kind of complex dynamics? And that's harder because a synapse is a bit more complex in its operation. So first off, let's try and understand what a synapse does. So I said earlier that a synapse is transferring a spike or an action potential from one neuron, which we all call the pre or the input neuron, to the next one. Now, if all we had to do was transfer it perfectly, then in electronics, that would be easy. We could just use a simple wire. But in biology, that isn't the case. What you find is what the amount of spike that is passed from one neuron to the next can be attenuated. So we make it smaller, and that attenuation we call the weighting. And the interesting thing is that attenuation isn't constant, but it changes through time as we learn and as our brain responds to different stimuli. So if we want to replicate learning, we need to replicate how the synapse changes its weight or its attenuation. And there are lots of theories about how this is done, and we call them learning rules. And so we're going to study one particular learning rule here, which is called the spike timing dependent plasticity learning rule. And this essentially tries to detect correlation between an input and an output neuron. So if the pre-neuron, the input, causes the post, then we essentially want to increase the effect of the input neuron. So we increase the weight. That corresponds to this right-hand side curve here. Essentially, if the pre occurs before the post, then allow in the future more action potential or voltage spike to go through. Alternatively, if the post is firing, if your output neuron is firing and your input isn't really firing at all, then we assume, well, the input isn't actually having much of an effect. And what we want to do is suppress the effect the input has on the output because we assume it's not correlated. So in that instance, we're looking at the left-hand side of this curve where we reduce the amount of spike that's passed through the synapse. So this kind of very simple learning rule can actually allow us to carry out computations when it comes to recognizing images and word spotting. If you combine neurons and synapses with this learning rule, you can build them. So synapses themselves need to be constructed, and you can build them out of circuits like we saw earlier with the neuron. But the issue with that is that they can be quite large, those circuits, and complex. And that's not good news, because synapses are much more populous than neurons. So we need the synapse to be as simple as possible. And so this is where our research comes into, from the team that I work in. What we want to do is build the simplest synapse you can possibly build. And for that, we turn to a device called the memristor, which we can see illustrated here. So what is a memristor? It's incredibly simple in its construction. It's just a metal, an insulator like glass, and then another metal on the bottom, as we can see in this slide. Now, in the ideal situation, that shouldn't actually conduct any electricity. Insulators shouldn't allow a current through. That's why you can touch a wire that has plastic insulation. But what you can do is make that insulator defective. You can create little vacancies in the crystal of the insulator. And these defects allow conduction to flow through, but also these defects can change with time. And so what you end up with is a very nonlinear system. And it turns out that the nonlinearities prove very useful in this case. Because when you look at work which was published by Adnan and Tony from within the group, and you look at the device structure, you can kind of start to see a symmetry. You've got your metallic conductive metal, which is very similar to the conductive dendrite, but which is just before the synapse, which is here. We also have your receiving neuron, which is conductive, again, down here. And you have that insulating barrier, which is semi-permeable to electronic current, which is the gap that is the feature of the synapse. So with that symmetry, researchers started to ask, well, can we actually do STDP? Can we replicate synapse behaviors? And it turns out that, yes, you can. So what we're looking at here is that STDP response, which we saw earlier, but this time produced by a metal oxide memristor. Essentially, you apply a spike either side, one spike on the top electrode, the post spike on the bottom electrode, and you're looking at the change in conductance, so how much current is allowed through. Now, you might notice that this STDP curve is actually flipped along the x-axis. That's not a problem. That's easily solved just by changing your experimental setup. So that's essentially what we're showing here, is that you can replicate synapses using these novel devices with barely any electronics, which is pretty cool. So if we zoom out now and look at the bigger picture, we have our neurons and we have our synapses. The question is, can we build neuromorphic chips? And fortunately for us, the answer has been yes. So what you're seeing here is a collection of neuromorphic chips. Most of them aren't using memoristic synapses, but they're using circuit-based synapses. And it's from some big industrial partners within the kind of semiconductor space. We have IBM, IMEC, Intel. So clearly neuromorphic chips can be built. The question is how well do they work? So there's a really nice study by IBM on their True North chip, which tasked their chip with two problems. First off, labeling images. So is it a cat, a dog, a plane? Secondly, word spotting. So if I say, hey Siri, have I said hey Siri, for example? And what they showed was that actually when it comes to the image processing, you can do labeling of images at a rate of 1,000 to 2,000 images per second. And that's very cool, because if we think in context, then that means you'd be able to essentially you'd be able to label frames on a live camera feed as it was panning across a scene. So you could imagine the camera able to label dog, bin, car, person, traffic lights, almost instantaneous in a video feed. What's even better is it worked, but it worked at a power consumption of 25 to 275 milliwatts, which is phenomenal because we're now working at the milliwatt power consumption range, less than a human, although we're doing a much more specific task than a human. And they even demonstrated this low power properties by running the application on a portable phone on a rechargeable battery, and it was able to run a couple of days continuously. Now, you may ask then, if we're able to do this, it must come at some cost. And so you assume that your cost would probably be the accuracy. Well, it turns out not really. So in this table here, we're looking at the accuracy of True North, the neuromorphic chip, on a range of different data sets. So these are images. And we can compare that accuracy against a state-of-the-art piece of machine learning approach. And what we find is, okay, yeah, there's a general reduction in accuracy, but it's usually about only 0.5%. And in some cases, it increases. So that's kind of good news, because it means that we're getting pretty much state-of-the-art performance at the lower power budgets. And Intel demonstrated this as well by taking their Loihi chip, their neuromorphic chip, and running it in a bunch of different machine learning tasks and data sets, and found that compared to a GPU, for example, they're 100 times more efficient in their inferences. And this power consumption advantage is also quite clearly seen when we look at the power consumption within all the different operating regimes of the chip. Because obviously the chip in your GPU is going to have a stage when it's running, but it'll also have an idle stage where it's not doing anything in between. And so what we see is that the neuromorphic chip with Intel, Loihi, is almost 2 orders of magnitude in terms of lower in terms of power consumption compared to a GPU in both stages, in idle and in running. So what that means is, when you look at the amount of energy required to identify a dog or a cat, or identify a word in a speech pattern, the amount of energy per inference is phenomenally smaller than that of a GPU. Of course, what this paints is a picture of neuromorphic machine engineering being a solution to all of machine learning's problems. Of course, there are challenges. So I'm going to finish the talk now just by looking at some of those challenges that we may face. So one of the biggest challenges is converting networks. And the problem of this is that in industry, deep neural networks and convolutional neural networks is what's been used. And the industry has developed using those kind of networks. And they are really quite different from the spiking neural networks we see in biology. So if we want industry to start taking these up readily, we need to be at a way to translate problems from this domain into that domain. And it may not always be the case that a problem is well suited to biology. For example, spiking neural networks are usually thought of as quite good for time-based problems. So we need to decide on what problems shouldn't need to be selected. The other challenge is in developing new learning rules. So we saw one particular one, which was spiked timing dependent plasticity. But as we build larger and larger networks, synapses become harder and harder to actually access in the physical network. So the idea of having versatile and varied learning rules is going to become ever important as these networks are applied to a variety of problems. And finally, a big one for hardware neuromorphic engineering is reconfigurability. In a normal machine learning application, your network is simulated in memory. So it's very easy to scale up, add in more neurons, remove them, modify synapse weights. When we're in neuromorphic engineering, we're actually building these networks. For that reason, it's a lot harder to occasionally add in neurons or change weights if they're hidden away amongst circuitry. So reconfigurability becomes another challenge. So yeah, those are the challenges that neuromorphic will face. And just to finish off the talk then, we have to address the biggest challenge that any new technology faces, which is the human reviewer. So what we have here is IMEX neuromorphic chip, a nice example, and it's going to compose some music for you. So it listened to a bunch of flute minuet from Belgium pieces, took it all in, used neuromorphic and STDP to generate this composition. So hopefully you'll be able to hear this. They'll put it in the chat if you can't. So there you go. You've just heard some music produced by some neuromorphic machine learning. Unfortunately, it did not get raving reviews from the music reviewer. It was derivative and very close to the chromatic scale. So people were not pleased. But that is a nice example of where neuromorphic is and where it might be able to go in the future. Just to finish off, I'd like to give acknowledgement to the team UCL that researched this, which is led by Tony Kenyon and Adnan Mohanic, who's chairing the session, and also the research staff. So if you're interested, feel free to reach out to us to learn more and collaborate. So that's it. Adnan, if we have any questions.
Great. Thanks, Dan, for that really nice and educational talk. So we have a few questions in our chat. I will try to go chronologically. We have some time, so I hope we're going to cover all of it. But if there are any more questions, please do use the Slido platform. You can post your questions. So the first question we got, it's a quite interesting one. So it says, is this the first step in an iRobot scenario where supercomputers start to outsmart humans and take us over?
I mean, ideally, that'd be great, because then I'm involved in it, so they might be a bit lenient on me. But I think what this shows nicely is that we can switch them off at the wall, or they'll run out of coal before they get too dangerous.
The second question is about this technology. So I guess this is about neuromorphic technology. When this technology will possibly catch up with the computational speed of a human brain?
Well, I think it depends on the problem. And if you look at the example we had with True North, able to label images at a rate of 2,000 images per second, you could argue that that's faster or at the same speed of a human brain. If I were to flash images of you of different objects and see how quickly you could guess what that object is, you probably wouldn't. I mean, I'm not entirely sure, but you wouldn't be able to operate that quickly. Your brain might actually be able to have little. In the brain, you might see a response that usually fires when you see a cat, but actually consciously, I don't think you could operate at that level. So I think in certain problems, it's already operating at the speed of the human brain. But in other problems, it won't be. But in the image, it looks like it is.
Okay, so the next question, what do you think about the promise of neurosymbolic AI? So that means to combine classical symbolic logic with machine learning. So we can then solve the problem of too much data training requirement.
I have to be honest, neurosymbolic learning, I know very little about, so I can't really comment on that, but it sounds really interesting. If that is one approach to reducing power consumption, then combining these kind of techniques will achieve really good results. And I think a key part of this talk is that neuromorphic isn't the only approach. We saw the TPU and also algorithmic advances as well. So yeah, symbolic logic sounds really cool. I got to read more about it though, for sure. Unless the speaker has anything else to say about it. I don't want to miss out on some fantastic tech.
Sure, maybe yeah, some additional note we might get. But okay, I'm gonna move to the next question. So this question is about dendrites and dendrite functionality. So it says, could we also replicate a dendrite which can reconfigure in 3D space? A connection that physically changes, thereby reduce the length of the signal travel. So maybe in general, you can comment on the importance and maybe feasibility of implementing dendrites as well as neurons and synapses.
Yeah, dendrites are really interesting because you could argue in the neuromorphic field they've been a bit overlooked. There's a lot of really cool computation which occurs in dendrites, as the questioner was saying, and the idea of actually changing the structure with time is an interesting one. In hardware, naturally that seems a bit hard. It's harder to rewire, change wire lengths or change where they connect to. But you could imagine having things where the weights are changed, like synapses, and you could essentially make the weight very high, or very low. I could make an element very resistive, and that would block off a path. So I could select between different paths by pruning, by changing the synapse from low conductance to high conductance. That's one way you could go about it. Like being able to actually change the path lengths. I think you'd have to do a special protocol, because obviously it's not so easy to modify the length of a wire. But why would you want to modify the path the signal travels? If it's because you want to change the attenuation, then you might not actually need to change the path the signal travels, but you just change a property of the medium it travels through. So if rather than traveling through a wire, it's traveling through a very defective oxide, so that it's almost conductive. If I could find a way to make my electronic path slightly more resistive, then we end up getting a broadening and attenuation, which is almost as if I'm increasing the spike's travel length, but I'm not. I'm just changing properties of the medium that it's traveling in. I think that's one potential way.
Then, okay, we move to the next question. So this was, has anyone looked at how the energy efficiency compares between memristors, neuromorphic chips, and old-fashioned neurons doing similar tasks? Yeah.
Ooh, I mean, I haven't come across a direct comparison in that sense. It's much more general. Adnan, have you ever come across anything?
Yeah, I mean, it's a very good question. If old-fashioned neurons means biological neurons, then it's very hard to do the exact comparison, because the biological neurons, we don't actually know how the brain works and what are the functional primitives of the biological systems, meaning a brain. We have some ideas, but then if we look into, for example, comparison between current implementations of artificial intelligence, of machine learning with the current hardware, that is then easy to compare with the, let's say, neuromorphic technologies, either with the CMOS or memristors or something like that. Then we can talk about what's. But maybe the very direct comparison with the biology would be a bit unfair, because we don't actually know how do we play chess or Go, what exactly happens in our brain. But we could maybe infer something. We know that on average, maybe human brain uses around 20 watts of power. And if we compare that with the systems that does a subset of the tasks the human brain does, there's a discrepancy in the power efficiency of many orders of magnitude. So that's the best I can do. Okay, so we have another question, which is about, is there any research into devices that would reconfigure themselves when facing a new problem? Or is this too advanced for today? So I guess this might be a selling point for memristors. So something I would guess, what's the question about something physically changing as there is some stimuli or a new problem that that device faces?
Well, yeah, so I mean, the learning rule, which we saw earlier, the SDDP one, is a good mechanism for that. If you can have a device which you can have operating without any change, maybe in a memristor, if you use low voltages, the properties of the memristor doesn't change too much. But as you increase the voltage, you start changing its dynamics and you start seeing that STDP behavior. So you have the ability then to use it in a low voltage regime where the dynamics shouldn't change too much. But then if you want to start learning again and start applying that learning rule, then I just increase that voltage. And now suddenly the dynamics of my memristor or whatever synapse I'm using starts to change. So yeah, that is possible. You've got to use online learning rules and you've got to be able to switch that learning rule on and off if you want to start adjusting and relearning. That is, I suppose, maybe one advantage to using online learning and neuromorphic, in that it can be adaptable. And if you can switch that adaptability on and off, even better.
Very good. We have one follow-up question. So I'm not sure, I haven't followed on which previous question this might be referring to, but it says, do you know anything about ferrofluids? I haven't heard of that, but yeah, I don't know, Dan, if you know anything about ferrofluids.
The most I know about ferrofluids is some YouTube videos. Why are they, do they have an application potentially? It'd be interesting to know if they do. Because we have there is a research in like ferro electric materials when it comes to synapses. That is another candidate. The candidate technology for memristors and synapses, a very interesting one. But ferrofluids, I haven't heard about. No, sorry. I feel like,
Yep.
No, sorry, carry on.
Fine. So there's another question. Is there a coding library or package for spiking neural networks?
Yes, there are a few. So if you're looking for almost a platform to run spiking neural networks on, there are, I think, brain scales is one where you can see you can implement their algorithms. If you go looking around, I can't remember the names off the top of my head, but if you whoever the question is, feel free to email me and I can forward you on to them. Also, there's a project called Spinnaker, which is trying to do spiking neural networks, but in the actual, rather than using, I suppose, neuromorphic hardware, it's using a more conventional digital electronics. And that's very cool because you're doing spike on neural networks with more traditional hardware. So Spinnaker would be another one to look at if you're looking for a platform to implement spiking neural networks on.
Yeah, I could just add that on GitHub, you have plenty of the open access spike neural network libraries. You can even check the things such as Intel's Loihi. I think they have put a few of those libraries there that people can play with and use.
Yeah, and if you go looking, actually, there is, I can't remember off the top of my head, but there's a university program where you can actually write code and run it on their neuromorphic hardware by submitting it to a remote server. But I can't remember what it's called, so I have to do some research into that.
Okay, I think that's it for questions. We just got the further description of the previous question. So ferrofluids as the artificially changing dendrites. It sounds very interesting to me, so maybe that's the new avenue. I think with that, we have finished with all the questions. So that's about, I think, right on time anyway. So I don't know, Dan, is there anything else you want to add or maybe elaborate on? This was really nice and educational presentation. I really enjoyed, although I've heard a lot of this stuff, but it was really nicely presented. So I don't know, do you want to say anything?
I mean, no, beyond like, thanks to everyone for coming to watch it. I hopefully you enjoyed it. And again, if you feel free to contact the research group for more information.
Yeah, indeed. I second that. So,
and thanks also, Adnan, for chairing the session as well.
You're welcome. So I would also like to thank everybody for joining. And of course, thanks then again for this very nice talk. What I would also encourage you all to do is to check the upcoming lectures by visiting UCL Minds webpage. You can find there all the future presentations and lectures. So with that, thank you all. Yeah, and stay safe.
Okay, we're off air.